This is just a quick reminder that you should feel free to pause the video if you ever feel you want more time to think and write. Welcome everybody to section 5.22, exponential functions and graphs. So one thing that I like to teach my students is something called growth factor, and it shows up a lot, especially on the SATs. If you think about increasing and decreasing something by a growth factor, it's actually really helpful. Let me show you what I mean. If you have $100 and you multiply it by 1.00, that's going to produce no change. It's going to have $100. But if you want to increase $100 by 1%, you can multiply it by 1.01. This 1 is 1% higher than here. You can think of this as 100%. This is 101%. $100 times 1.01 will give you a 1% increase. This is how you get a 2% increase, 1.02. You can multiply it by something less than 100%, say 99%, and multiplying something by 99% or 0.99 is going to be the same thing as a 1% decrease. And here, 98% is 2% less than 100%, so multiplying it by 0.98 will give you a 2% decrease. If you think about these things, you think about what this looks like here, $50 shoes on sale for 20% off. What that really means, 20% off means you want to only pay 80% of it. So a 20% decrease, you'd have to multiply it by 0.08. I say 0.80. $50 times 0.80, and that's what it would be. The original times the growth factor. Here, if you want to increase it by only 5%, then multiply it by 105%, so 1.05. That'll keep the 250 and increase it just a little bit, 5%. You can even do this multiple times. You can increase it by 7% and then by 15%, like this. $75 increased by 7%, increased by 15%. And the order actually doesn't even matter. It doesn't matter which order they go in, because if you're multiplying all of these three things together, you'll get the same product anyway. Now, if you put money in the bank, you'd say you gave it 3% interest on $1,000 for every year for 3 years. That would look like this. You've got $1,000 and then 3% interest, 3% interest, and 3% interest. Another way to do that, if you want to kind of combine them all together, 1, 2, 3, 3 of these together would be just one of them to the third power. And this is actually, we're going to get a formula out of something like this pretty soon. What if you wanted to get 3% interest on $1,000 kind of spread out over 3 years? You get 1% of those 3% each year. So what you could do is you could say, well, you're getting $1,000 and then 1 plus, all of these have 1 plus if you're increasing, and then 1 plus your 3%, but divided by 3, so 1% each year, so you do it 3 times. You're going to get it 3% overall, spread out over the course of 3 years. You'll get 1% each year. Anyway, this is how you get a formula. If you look at this formula for compound interest, it's going to be the same thing. It's going to be that the amount of money you have at the end is going to be equal to the amount of money you started with, times 1 plus your interest rate spread out over how many pay periods, and then this is going to calculate how many pay periods you have. Here you can read it. The final amount is going to be equal to the starting amount, the principal, and then T is years in the bank, R is the interest rate. Use a decimal, don't use percent. And then the number of times of interest compounded in a year. So what that looks like would be like this. $100,000 is invested at 6.5% semi-annually. Change the 6.5% to a decimal. And then semi-annually means twice a year. So you're going to cut this out, spread this 6.5% over the course of 2 different payments in a year. And then raise to 2t. What about quarterly? Well, quarterly means 4 times a year. So you have this 6.5% divided by 4, and then there's a 4 up here also. What about monthly? If you did it monthly, it would look like this. The percent spread out over every month, and then 12t. That's, if you had like 3 years, it would be 12 times 3. That would be 36 times you're receiving the interest. So it's an interesting question to ask. The starting amount, let's say you have a starting amount of $1 and 1 year of the bank, and you were eventually going to get a 100% rate, but it's going to be spread out over a certain amount. What happens as the number of times the number of times the interest is compounded every year? Let's say you just get interest one time a year on that $1. Remember, we're going to spend 1 year in the bank, and we start out with $1, and we're going to get 100% interest rate. If you just get interest once at the end of the year, your amount will double. Because you start off with $1, and then you get an interest of $1, so that's $2. If you do it semi-annually, you'll actually get more money. That's because you have more payments. If you did it 4 times a year, it would look like this. You could see that these n values are increasing here. We're going from 1 to 2 to 3 to 4 to 5. And up here, they're also doing the same. In fact, this is what it looks like in the simplified version. $1, 100%. This is written as a decimal, 100%. And then since t is 1, we're only going 1 year. That also kind of evaporates as well. It's just an invisible, unwritten 1 right here. So the only thing that we're changing to get new values, new final amounts, is we're changing the number of times that you get compounded interest. If it's only once, then 1 is here and 1 is here, you get $2. 4 is this. 5, let's say you broke up the year into five different spaces, then you'd get this amount of money. Like here, the more compounding periods you have, the more money you're going to get. If you got interest 365 days a year, like at the end of every banking day, they gave you 1/365th of all of your interest, then yeah, it would get more than before. And if you did it every hour, like the 365 times 24 hours a day, if you got interest every hour, it would look like this, 2.7181. Although the numbers are getting larger and larger, they're not going to get larger forever. In fact, it's going to look like this. If you plot the values of that table, then you'll see that eventually it gets higher and higher, and eventually you approach this horizontal asymptote. Where is the horizontal asymptote? It's exactly right here. And we're going to give it a letter. The letter is going to be E. This letter is so important that if you, for example, this is a screenshot from Desmos. If you just type the letter E into Desmos, it will give you out the same thing we have here, the same number we are approaching here, 2.7, 1828, 1828, 46. It's an incredibly important number, and it has lots of applications. It's kind of like pi, really. Like pi is 3.141592653, and it keeps on going. And it's used in a lot of geometrical applications. Well, here, this number is going to be used in a lot of exponential applications. So much so that it gets its own letter, just like pi gets its own letter. Pi, actually, the symbol that you write is the Greek letter P. This is going to be the English letter E, and it represents this value. E is just a number. At the end of the day, the one thing you really need to remember is that E is just a number. It's an irrational number. It's a crazy number like pi, but it doesn't, there's no repeating decimals anywhere. But it has lots of applications. It's just a number. So most calculators have E's. The iOS iPhone app, the calculator app, has E. And if you type E and just hit enter, you'll get this. E to the first power, and it'll give you 2.7182818. And then you have to round it. And the instructions for this particular example say compute each of 4 decimal places. So you've got to round. You look at the 5th decimal place, and you see it's an 8, so you round the 2 up to a 3, and that's it. E cubed would be this, and you see the 3, and it rounds down to just this, 4 decimal places. So I want you to find a calculator or type it into Desmos and figure out what e to the negative 0.23 is. Now it might also be a really good time to tell you that all computers have a silicon chip, and silicon is your element audio check for today. if you type in e to the 0, that's just going to be 1. And any number to the 0, any positive number raised to the 0 exponent is going to be 1, and that's no different for e. Because remember, e is just a number. E is just 2.7, 18, 28, 18, 28. If you take this number and you add 1 to it, this becomes 3.7, 18, 28, 18, 28. And you round it to the 4th decimal place, you get 3.7183. E to the 6th, exponents, example 6 here says graph each using a table or transformations. So here, we got e to the x. Remember, we've had 2 to the x before. Not a big deal. We'll have e to the x. E to the x is going to be, if you have a value of 1, then it's just the value of e. It's 2.7, 1828, 1828. Here, e squared is that number squared, is 7.4. And e to the negative 1 is going to be 0.4. E to the negative 2 is going to be 0.1. You need to calculate these with a calculator, but in the end, this is what they look like. And you can draw the graph. Now, I want to take a look and see what happens to these particular values. I highlighted this yellow with 0.4, so we can compare where it is over here. Yellow 0.4, green 2.7, green 2.7. If your function, sorry for the scribbles, if your function is e to the negative x, then that's kind of like the original function f to the negative 1. Now, we know this is going to be a horizontal reflection. And so, comparing it to the original, you can see that the green and the yellow got swapped. Here, the original was, the parent function is going up like this, and the horizontal reflection is going down like this. It's decreasing, because this point gets reflected over here, this point gets reflected over here, this point stays, and these points get reflected as well to the opposite side of the y-axis. Example C, what if we did this, negative 0.5 x? And this is the same thing as, if you can't see it, it's negative 0.5x is the same thing as x over negative 2. That means we've got a b value of negative 2. It's going to be a horizontal dilation by a factor of negative 2, as you can see right here. Things are going to be spread out. Not only are they going to be reflected, they're going to be spread out twice as far. So the green and yellow points, green 2.7 gets reflected over here, and yellow 0.4 gets reflected down here. You can see not only is it a reflection like before, it's also a dilation. It got spread out wider. Here's what just a straight up horizontal reflection looks like. This is a horizontal dilation by a factor of negative 2, and all these values are twice as far away. G of x is equal to 1 minus e to the negative 2x. Well, we've got the same that we've got before. I see a b value, like we said before, of negative 1/2, of c value of negative 1, and a d value of positive 1. That means we're going to have all those different things going on. We're going to have a horizontal reflection, a vertical reflection, and a vertical shift. And you can see them here. That's imitated right here. You can also just use a calculator to calculate these values, and this is what you get. Anyway, I'd like you to start assignment 5B2, copy the problem list, and do the first problem, and I will see you in class.